Oh, gee, the projector was working either. Didn't realize that. Hopefully it starts soon. Oh, yes. Okay. All right. Shall we get going? So we can go to, in my case, it's my last class before the break, so happy. Okay, so yeah, a mistake was found in the assignment. So at some point I write the matrix I minus x prime minus 1x. So I forgot to add a prime at the end. Please add it. So I'm going to first change it because otherwise you cannot do anything with it. So it's what number on the third question? Right. Okay. Otherwise, let's continue with limits. Very good. All right. Okay, so I'm going to tell you some stuff about how you solve limits, not all of them. There's a nice thing that was found by L'Hôpital, which is called L'Hôpital rule. L'Hôpital rules, no, L'Hôpital's rule, which you may find out later. I'm not going to teach it. Here's just what you're going to need for to solve any sort of derivatives you might encounter. What? No. We won't. What I'm saying is, yeah, there are other things above what we're beyond what we're going to see that, yeah, that you may have heard of, but we don't have time to see it. So if you really care about it, ask me. I'll go and make it. Okay, so here are the basic rules that go on. One, if you have the limit of some constant, well, you don't need to lose too much sleep on it. So the limit of whatever else, yeah, I'm going to towards C of k equals k. So let's add in a bit more stuff. So the limit as x goes to C of x is, yeah. So that's also quite simple. So now we introduce our functions. So if I have k that multiplies some function of x, here, then it's going to be equal to k times the limit of that function. So I can take the k out of the limit operator. So that's pretty handy. All right, so same with exponents. So if I have f of x to the n, where n is some exponent, then it is equal to the n. For
continuity.
So when you have a counterexample, then
So, like, for example, we have like two countries functions that you can think of as inside the function.
yeah. So yeah, exactly. So this what's going on there is not multiplication by a scalar is itself a function that is continuous. So it's going to work. And taking the exponent is the same. Yeah, exactly. 4. Need not write everything down again. Oh, so that was 4. Sorry. Yeah, 5. Yeah, addition of functions. So if I have f of x plus g of x, then I'm going to get, so addition itself is a continuous function. So I'm going to, so it's the limit of f of x plus the limit of g of x. All right. So nobody's struggling to copy stuff. 6. No, 6. It's yeah. Okay, no. I'm rather going to see to introduce this as a quiz. Use previous properties. What did I want to show? Oh yeah, just the show that this equals to so this is just to make you a bit practice your proving skills. Oops, that's not the case. So it makes total intuitive sense, but just so in math we like to be very cautious about saying, oh, so this step there, this is what I use. This step there, this is what I use. So please think for like a minute what properties you would be using, and so what sort of steps you would be using to show that, and then I'm just going to go ahead and show. This is free to indicate the sort of things I would like to see when I ask something like in the homework. Please demonstrate this or that. We are always we take shortcuts because we assume that everybody knows that this is true, but mathematicians, whenever you say obviously, they say, "Are you sure?" Okay, so what previous properties would I need for that? Which one?
3 and 5.
Yeah, awesome. 3 and 5. So let's just change this. So this is equal to simply just going to rewrite it in a very simple way. So plus, and then what I have here is a scalar multiplication of a scalar, which is -1. Then this is equal to the limit of this plus the limit of that. In a sense, what I have done here is sort of redefine the function g of x as the function minus g of x. So, so this you would say something like using property that's 5. and then we're not done. What we can do is say that this is like a scalar, so we can take it out. So that would be using property. So this is the sort of way you do it formally. So we can, I guess most people can guess that it is true, but so just to be absolutely sure. So, and in a way, it's nice because that's always what we're trying to do is to assume the fewest number of things and show that everything else just is a consequence of what we've assumed. So we don't have to, so because in the previous slides when I took the class over, so this was another property and I'm like, come on, you don't really need it. You just use something that came up before. All right, 6. Oh yeah. So yeah, this let's call it 6. 7. So same idea with products. So the limit of the product is equal to the product of the limits. And then I could go on with add some simplification there for fun. Then 8, quiz again. Use the previous properties. Show that. The limit of x divided by g of x equals, to make this up. Yeah, that's how. Equals to the limit of f of x divided by the limit of g of x as long as that, yeah, this is that. So use similar, oh, so maybe if you didn't write down, so put this in your memory. So the question is how you would you find the limit of a quotient using prior properties. And the prior properties are these ones. Yeah, so it's on this screen. So think about it for 5 seconds, 10 seconds. Then I'll just write it. Okay, so somebody else. Which properties should I be using to demonstrate the 8? Because I know somebody has the right answer. But... if I want to demonstrate this, what sort of rules should I be using? They're right around here. Yes? Yes, and rule what? Yeah, exactly. Awesome. See? So let's do that. This is, well, it's, and And also, as I was saying, it's not easy to prove stuff. So when you look at some ways of doing something that seems to be working, it's it there's a very big chance that if you want to do something similar, then you're going to do it in a similar fashion. Because in a sense, if you just took logarithms or exponent, then it's the same principle. So let's go ahead and do that. So we're just going to rewrite this way. Exponent minus 1. This will be equal to that's property 7, yeah. And then oops. This would be using property. Yeah, 4 exactly. Again, always assuming that I can divide. All right. So now we're getting to more important things. Or not more important things, but important things. Limits at infinity. So when we say at infinity, we only mean towards arbitrary large values. So I'm not going to go into any discussion about what is the profound nature of infinity. That's not the point. So category 4. Oh yes, so that's so let's just give you an example, and it's going to be pretty clear what you have to do with it. So when x goes infinity of 7x 3 plus 2x plus 1 divided by 3x. So if I just told you x is a infinity, well, it doesn't really mean all that much anyways to say that x is infinity. Yeah. We don't know what it means. But how can we deal with this? So here's how you do it. So the trick is to always, if you have some expression in which you have some value that goes to infinity and some other value that doesn't go to infinity, then you can be very sure that the value that doesn't go to infinity is just going to be squashed to non-existence and going to not matter that much. So you can just rewrite it this way. So you look for the variable with the biggest exponent, and you can just put it in front. So, and then what you can see here is it's possible to just divide these two. All right. So divide them. And then here I get 2 divided by x. So 2 divided by x, when x is arbitrarily large, then what is it? It's 0. And same thing for 1 divided by x3. So you just get 7 divided by 3. So that's how you solve it. That's most of what we're going to do is either limits when we have 0 over 0 or infinity, but for which it's possible to do some trick like this to get rid of what's unimportant and just keep what's important. All right. So another example. So just to practice yourself. So plus 3 times x squared minus 1 divided by x squared. So please tell me what this is. Yeah, infinity. One easy way to see it is to simply multiply it, and you're going to get this sort of expression. But there's also another way of looking at the same thing, is asking yourself again, when x is extremely large, does adding a small puny 3 matter or not? But it does not. So you can perfectly write that this thing on the left is absolutely equal, since I'm going to the limit, as this thing on the right and as this thing on the right. It sounds outrageous, but it's perfectly fine since I'm taking the limit. And then what am I getting? I'm getting x, so I'm getting infinity. Because here I divided by x2, so I'm getting something that's very large. Yeah, I had that other one, but who cares? It's the same. Yeah. You're going to practice on that, but it's not. Plus, we're going to do a bunch of other ones when we find out all the rules of derivatives. So I think that's good. So yeah, last question before we move on. So that's all I have to say about the limits. All right. So, and if you're stuck with more complicated non-algebraic or non-polynomial expressions, then there is L'Hopital rule. Ask me if you need it, but yeah, I'm not going to bother you with that.
Did you cover L'Hopital?
No. I'm just saying that's not the end of it, because you're going to get into trouble anyways with if you have different functions of different things, and yeah, this is just polynomials. Okay, so let's move to some different topic. Digression on inequalities. I can't remember why we're doing this, but it's fun. It's a fun change from what we were doing before. Inequalities. So let's just discuss what everybody knows, but in a more organized manner. So some rules. So if A is larger than B. Oh yeah, and do I want to system A? Yeah, and C is greater than 0. That's important. Then addition. So yeah, let's stick with the format we had. So A plus C. So if I add C on both sides, is going to be greater than B plus C. So here I start with A is greater than B, and if I add the same thing on both sides, then it shouldn't change the sign of the operator. Then subtraction. Yeah, so that's a bit redundant. Sorry about it. I didn't change it that way. So if I subtract C, doesn't change. Multiplication. AC is greater than BC, and this is because of, remember this. Because I'm going to discuss multiplication by -1 later on. Division. So A divided by C is greater than B divided by C. And again, C is non-zero, especially, and it's positive. 5. Squaring. So this might be more original, but so if I know that A is greater than B, then oh yes, but it's more subtle than this. So A squared is greater than B squared, provided that if B is greater than 0. So otherwise that wouldn't necessarily work. So if so for instance B was smaller than 0, then you could have something that like 2 is greater than -3, and then of course 4 is smaller than 9. So that's why you absolutely need the B to be greater than 0. Next one. Oh yeah, multiplying by -1. So I'm going to get that minus A is smaller than minus. All right. So that covers all the cases where C is smaller than 0. Then you just have to have -1 times C, and you can cover these cases. So I'm not going to go into detail. Transitivity. I didn't put a number on that, so let's say this is 7. Transitivity. So if A is greater than B, and B is greater than D, then A is greater than what? D. Okay, and now final point I want to make is now all these are the previous rules. Apply weak inequalities. We need smaller than or greater than. or equal. Okay, so just a small exercise for you to do. So, example, solve the following: 2x minus 1 is smaller than 9 plus 6. So simplify this expression, please. And this could be even more general than this, right? That works. Just look at that. Yes? The one? Do you mean to answer the question then? Oh yeah. So sorry, that's multiplication by minus 1. So what's x? Is it greater or smaller than something? Yeah, good. So let's do that. So let's subtract x on both sides. So I get x, and then let's add 1 on both sides. So 10. So that's okay. Questions about this? No. Easy peasy. All right. So that's a easy class before the end. So another digression on absolute values. That one may be a bit less familiar. So let's go for it. So some properties. So what does it mean to have the absolute value of something? So absolute value of x equals okay. So it equals to x if x is greater or equal to 0, and it equals minus x if x is smaller than 0. And of course, you could write 2 is smaller or equal, greater. Yeah, exactly. So here I had a big discussion with my roommate the other day, who does some scientific stuff too. And so what he says is, what's important is that you have one rule for one number. So you don't have a single number which has no rule or two rules, because otherwise you cannot choose. And by default, you include the 0 in the positive interval. But it's just a convention. You could do otherwise. But yeah, I would.
There's even a philosophical debate about whether it's positive or negative.
Yeah. So it's above what we should care about. But back then, I thought, so I could perfectly write smaller or equal there. There's nothing wrong with it. In a sense, yes, it's like more complete, or who knows. But yeah, the way to do it is to be sure to cover the whole interval, but not overlap.
Have you ever seen somebody write like x written there, that x equals 0 for x equals 0?
Yeah, so you can do that also, because yeah, you have if you have a special rule for 0, yeah, go for it. So yeah, I'm not going to be too mad if I see that you. All right. So some properties for any two real numbers x and y. So absolute value of x plus y. Then, so if you say it's easy peasy, I'm going to let you think about it. So what should be my sign there? Think about it for a while. It's once you have it in your head, it's trivial, but just looking at it there, you must think about it for a while. You're sure it depends? Yeah, it's bigger, almost. It's bigger, almost done, almost this. But so I'm going to give you an example. If you have 3 plus 4, you have absolute value. Then on the other side, you have value of 3 plus absolute value of 4. In that case, that's equal. Yeah. So it's yeah. So this is smaller or equal to that. So it could be the same if both are positive. But if one is positive, one is negative, or both are negative, yeah. No, it's if they flip sign. Yeah. So yeah, that's 1, 2. Multiplication. So x times y. Good to torture your brain a bit just before the break. Yeah, it's exactly the same. So here there's no inequality for whatever x and y is, because anyway, the only thing that matters is if I have something that's negative, I just put the minus front and 1 in front, and it disappears. So yeah, 3. So and yeah, let's go with division, but that's the same sort of deal. So x divided by 1 by y equals x, provided that yeah, y is not 0. Good. And now convert this. So this I hadn't done that before I started teaching this. So for you it should be quite maybe absolute values into inequalities. So if I go back to my definition, so I'm going to have that absolute value of x is smaller than n, implies that minus n is smaller than x is smaller than n for n is greater than 0. And just having weak inequalities too. So how's that the case? Well, we just had to think about it. So if you see the absolute value of x is smaller than n for some, of course, positive number, otherwise there's just no solution. So what does that mean? Well, imagine that, so example. So n equals 10. So just putting there an example, it just makes things super clear. So it means that this will be true as long as x is 10, 9, 8, 7, or not 10 exactly because I have weak. But so it's going to be true if I have anything below x must between minus 10 and 10. Yeah, depending on this which case I include or not include them. And it means that essentially you can convert absolute values. If you have operations with absolute values in them, it's bothering you, you don't like it, makes you feel uncomfortable, then you can just get rid of them and solve it in a easier fashion. So let's go for it. So, example. So if you have an expression like absolute value of 2x plus 5 is smaller than 3. So find a simple interval for x. Negative 10. No, I haven't heard. Oh, yeah, one is one of the intervals, and 4. Yeah, good. All right, so let's do it. So I'm just applying my formula there. It's you just apply the recipe basically. So I have that. So x here is not x, it's 2x plus 5. That is greater than minus 3 and smaller than plus 3. So we can solve both sides on this. You could do it one side and then the other, but then we can solve everything. So let's, what shall we add? Yeah, minus 5 everywhere. So I get minus 8 here. And then minus 2. And then I can divide by 2. So minus 1, 4. Then I can multiply by minus 1. In that case, so I get that minus x is greater than 1 And oh, does that make sense? I think I made a mistake somewhere.
My mistake. When you send 5 to the other side, it should be +8. Sorry, it should be 2 on this side and 8 on the other side. Then it would be like 5 minus 3 and 5 plus 3.
Yeah, -3 plus 5. Oh yeah, I added 5. Yeah, I should subtract 5. Yeah, okay. No, it's no. So the thing is, in my example in my notes I had -5 here. Yeah, okay. So that okay. Sorry about that. So I was yeah. So no, this is the right answer. It's just let's do it like in my note. So yeah, +5. Yeah, 2 and 8. Yeah, so that's simple. Well, actually, I here I got to use some other rule that was even better. But, all right. 1 and 4. Okay. Yeah, try it yourself with the minus. So you should be able to do it. All right, so that's good. So we go until 2:30, right? Yeah, that's about right. I think I'm going to be. Oh, we'll see. Okay, so any questions about this? So that's a neat trick. Once you just see this rule, then you can apply it, and yeah, it gives you, yeah, it saves space. All right, so continuous functions. What they are here, I think I go a bit farther than in the book, but you know, not that far. A function f of x is continuous in x0 if so 3 conditions. F of x0 is defined, by which I mean x0. I can't. No, don't be sorry. That's I know that I'm on the right track. Yeah, right. To the limit when x goes to x0 of f of x is defined, and 3 the limit when x goes to x0 of f of x is equal to f of x0. So that's a very technical way of saying this. Yeah, exactly.
You don't need to write this on the paragraph.
Oh yeah, no, yeah, sure. Properties.
For the record, the second condition implies that the left and right hand limits have to equal.
Yes.
For that it's not.
Yes. Oh yeah. So that's something we saw last class. So. Okay, so properties f of x is continuous. So that's really just stating stuff. Sorry, it's a bit boring, but it's perfect. Is continuous on an interval if it's at every point on this interval. Is a continuous function if it is continuous for every x of its domain. This is what it means to be a continuous function, and we have a lot. And then, so this is all abstract, but now if you want to just look at it and know whether it's continuous, so that's the easy thing to do. So geometrically, a function is continuous if its graph may be drawn without lifting the pencil. From the paper. So we have this definition because functions and continuity have been discovered or invented when paper and pencil existed. Otherwise, we might see when the rock don't have to be lifted from the clay tablet, for instance. But yeah, here is what it is. So if you can draw it without lifting your pencil, it's continuous. Example. So if I have f of x equals x4 plus x2 minus 4x plus 4. So is that continuous? Yes. So it's just a sum of continuous functions. So x4 is continuous, x2 is continuous. So I'm going to mostly say what can go wrong. So you can be on the lookout for what may be wrong. But yeah, if you look at just something polynomial like this, no worries. It's yeah, it's pretty continuous. All polynomial functions are continuous. So what can go wrong here? Example, if I have f of x equals to x squared divided by x squared plus 1. So here, yeah, you have something weird going on here. So you might be on the lookout for something. Or not. Oh, or not.
-1 x squared minus
No, but so that one is continuous. So yeah, is continuous again. All right, so I thought that was my counterexample, but no, it's perfectly fine. Yeah, so let's actually go and draw that. Squared divided by squared
At
plus
the
1.
bottom, it never equals 0.
Yeah, exactly. Yeah. So what is, yeah, that's perfectly fine. We can draw it out everywhere and you never have to lift your pencil.
Right, it's minus 1, then
Yeah, exactly. So let's continue this. Okay. So do I get to a problematic case later? Yes, okay. Example. Yeah, could be the same or different. So yeah, let's just use the same, but flip -1. Is not continuous because well, if x plus 1, it is indifferent. Or yeah, it's true. So well, let's go back to our nice friendly rule and show us why this is wrong. Um,
plus and minus.
yeah, so I'll enlarge. Oh,
The same out there.
but so what's wrong with, no, it should, oh, okay, yeah, okay, there it is. Okay. Yeah. Well, actually, it's not so easy to see, but yeah, so you cannot draw this with your pencil. You need a computer to do it for you. Or you, rather, you could draw it with your pencil, but you can't draw it in one go. Yes, students last last semester, they were very lucky because they had online exams. So I hope it did take advantage of all the nice tools like this, to at least check the functions that they were dealing with. In your case, that's not going to be possible, sadly. Okay. Um, yeah, and I should add and the limit exists. Plus or minus. Victoria, you're in my space. Compositions of functions. So if so, that's a sort of a something that was a theme that was going on everywhere. So what's going on there? What can I do with the functions? So if f of x is continuous in x equals x0, and if g of x is continuous in g of y, sorry, in y equals f of x0, then g of f of x is continuous in x0. Right? So if you have one continuous function and you apply a second one, as long as it's continuous in the domain that you're going to get from the first one, then the composition is going to be continuous as well.
That's because f is a composite function.
Well, you see that h of x is a composition of g of f. Yeah. But that's just semantic. It's not so interesting. But so again, that's going to be useful for stuff that we're going to see. So, and now we're going back to differentiability. So continuity and so every differentiable function is continuous. On the other hand, not every continuous function is differentiable. So differentiability needs two things. So you have to be able to draw your function with your hand, but also you must draw it in a smooth gesture. So you must not have kinks in it. If you have kinks, it means that you cannot take the slope at this point. Yeah, or yeah, exactly. Yeah, so continuity condition is the following. So, f of x, so an x equals f of x0, and then the differentiability condition. So that's what f prime of x equals to the limit and delta x equals to 0 of delta y divided by delta x which is also equal to, then if I substitute back what my expression was initially, so I have f of x plus beta x minus f of x exists at x0. So, this limit must exist, and it's not always true that it exists. Yeah, it depends. Depends where. So, just saying a bit the same thing, but differentiability is a more restrictive condition than continuity. Continuity at every point. Presents gaps. But differentiability, well, I could say continuity at a point. Those are the presence of the gap. But differentiability point rules out the presence of a point. So, example. Oh, I know that was useful. So, my absolute values example. So, f of f prime of x equals to No, I think I didn't mean to write this f of x minus 2 plus 1. So what should I do with this? So I have an absolute value. So what I'm going to do is rewrite it in terms of sections and deal with every section independently. So f of x is going to be either x minus 1 for x is greater or equal to 2. And it's going to be minus x plus 3 for x is smaller than 2. Maybe I went a bit fast there. So what's going on? Well, either x minus 2 is greater than 0 or smaller than 0. So if it's greater than 0, then it means that the absolute value doesn't change anything. And I have x minus 2 plus 1, so x minus 1. And if it's greater than 0, then it means that x has to be greater or equal to 2. And the other case is the other case. So if it's negative, then it means that I have to take a negative sign of it. So I get minus x plus 3, minus x plus 2, plus 1, so minus x plus 3, all right? And so doing this is just a sure way to make sure I'm not making any mistake. So I had the graph there. Okay. Somebody knows if this works, and no, it doesn't. Perhaps. Oh, apps. Oh. It was a pure guess. All right, so that's what it is. Okay. So I'll just leave you with a quiz. What is f of x equals 1 over x differentiable at x equals 0. Well, essentially, we have already said it. I said that you have to be continuous to be differentiable, and it's not continuous at 0. But so I'm just going to even go further and write what would happen if you were to do that. So no, since it's not continuous. And let me just show you what happens if I compute this. So I get 1 over x plus delta x minus 1 over x over delta x. And here you already see that there's a problem there. So I cannot have I cannot estimate it at 0. So you're stuck. You cannot have any. Is wrong. Is the only thing I can say. Okay, so all right, I'll stop here for now, and we're done, right? Yes. Yeah, we start at 1:15. Yeah. Okay, so have a good break, and email me if you have any question about the assignment. And, yeah.